Good morning, everybody. Let me first of all thank the organizers, Pinaki Chowdhury, and no, it's not working, no? And Purushottam, right? Well, I continue. So let me just thank you for the invitation. It's really a nice opportunity to be here. It's my first time in India. So I am enjoying very much what I have seen so far. It's really, I am enjoying it. I also feel rather honored because you gave me the first talk. So this is also a responsibility. I hope that you like it, okay? So let me see if this works. So the title of the talk is Labquakes, Failure of Porous Materials Under Compression. And this is a work that we have done in the University of Barcelona during the last 5-6 years. In collaboration with my colleague Antoni Planes, who is a professor there, but also many other people. There's people, this student, Yang Chu, that came to Barcelona, but he's from the Xi'an University in Xi'an, and the professor there, Xiangdong Ding. Then the second part of the talk, we have been collaborating with María Ángeles Gómez Borrego, who is from the Institute of Coal in Spain. Then Daniel Sotoparra from Mexico is a postdoc that comes and visits us often. Then the people in the Center for Mathematical Research near Barcelona is Víctor Navas, Isabel Serra, Jordi Baró, and Álvaro Corral. And also then Professor Eckhard Salje from the University of Cambridge that had the original idea about measuring this kind of problems. And Guillaume Nataf, which is also a postdoc that comes often to Barcelona to visit us. As the title is suggesting, this Labquakes, it's experimental work, and quakes, it's really connected to geophysics. So I don't know what is your knowledge about geophysics, but there will be an introduction on that. The name, by the way, is not in the dictionary. That was invented not by us, but by a geophysicist, this Ian Main, who is in the University of, is in Scotland, in Edinburgh. He suggested this name after reading one of our papers. So let me see if this is working. Okay, this is the outline of the talk. So first, this introduction about geophysical aspects. I will go slowly because we have to understand these laws here that then we will apply for the analysis of our measurements. Then the experimental setup, the kind of measurements we do, that as you will see is this AE stands for acoustic emission, is the kind of measurements we do. We have studied many samples, but here in this talk today I will focus only in these bicore results. That is the first kind of system that we were studying. And also I will add some very recent results on coal and charcoal. And I will then finally finish with a summary and some conclusions. Okay, so let's start. First of all, this is the take-home message. So if you understand this, you can already skip the rest of the talk. Okay, Labquakes are these acoustic emission avalanches that occur during the uniaxial compression of porous materials. And this phenomena shows evidences of criticality. Criticality meaning lack of characteristic scales. This means that these properties, they don't have a typical value, but they span many scales. And as you will see, this problem also has strong similarities with real earthquakes. Here I have compared the typical dimensions or the typical scales for real earthquakes and Labquakes. As you will see, earthquakes have energies. Well, there are earthquakes of all sizes, but the ones that are measured and the ones that worry us, they have energies in this range between 10 to the 10 and 10 to the 18 joules. Whereas our experiments, the energies we are measuring from our Labquake events are 10 to the minus 18, 10 to the minus 11 joules. So there are 30 decades difference between the energy scales in the two phenomena. Concerning length, okay, earthquakes, okay, you can think that the earthquake is a phenomena that affects global, so it can go up to the radius of the Earth, but the smaller faults, let's say, can be 100 meters or similar things. In our problem, as you will see, the samples are really small. They are centimeter or millimeter samples, And what the cracks we are producing there, they are in the micrometer scales. So there's 10 decades difference in length. And concerning times, it's also difficult to compare, but you may think that earthquakes, they last very short, but short means seconds, somehow. And then our available catalogues, so we have been studying earthquakes from a century or something like that. So the length of our analysis, or temporal analysis of earthquakes is of the order of 1 million hours. As you will see, in our experiments, we are able to resolve less than microsecond scale for the duration of the events, and our experiments last for 1 hour, 2 hours, like this. So there is this big difference in the scales between the two phenomena, but despite this big difference in the scales, there are strong evidences that both can be described by the same laws. And this is, again, a self-consistent proof of that this is a critical phenomena, because it's invariant when you change the scale, and this is the best proof for that. You have the same from 10 to the 18 joules down to the 10 minus 18 joules. This is the message that I wanted to transmit. Okay, so now a little bit of introduction to maybe things that you already know about geophysics, but essentially in geophysics there are like two schools, or like two extreme schools. One that I can call it a holistic approach, and the other one which is reductionist approach. Holistic meaning that you can look at the earthquake as a global phenomena, you just want to see if there are some patterns, reproducibility, some statistical laws governing all of them. And reductionist approach means you focus on a particular fault and a particular place, and then you try to measure their forces, what displacement exactly, what are the characteristics of that rock there, etc. It's true that none of the two approaches so far until today has been successful in predicting earthquakes. This is the final, of course, this is the final goal that we all want to achieve. But I will use this holistic approach. So I am attaching this, attacking this problem from a statistical analysis point of view. Okay, so I see just the earthquakes as a point process, what is called mathematically a point process. So essentially, I consider this as almost instantaneous phenomena that occur in a certain time, a certain given time, tk, in a certain location on Earth, latitude and longitude, or whatever you want. Maybe if you want depth, you can add depth. And then with some properties. I will focus mainly on the magnitude, but not, in fact, the magnitude of the earthquakes can be measured by different ways. I'm not going to discuss that, but this magnitude, there is a general agreement that can be easily translated to an energy by this formula. So the magnitude is measuring something proportional to the log of the energy. Energy meaning the energy released when the earthquake occurs, okay? So essentially you can represent that schematically. If you just forget about the position, just imagine time and magnitude as a time sequence, and then the earthquakes have different energies like this, okay? So this is the time sequence of the earthquakes. Then, again, forgetting about the positions, because as you will see in our experiments, we don't have access to the epicenter or the epicenter of the, we just have access to time and energies. So then we forget about that. If we concentrate in time and energy, the description of this point process can be done by a series of statistical laws. These laws are here. These are Gutenberg-Richter law, Omori law, productivity law, and unified scaling law. These laws, the four laws, somehow contain some evidence of criticality because they are power laws. And when you have a power law, it means that you have something which has no typical scale. Okay? And these laws, when you have a power law, they introduce an exponent that characterizes the decrease of the power law. The Gutenberg-Richter law, that has to do with the distribution of energies of the earthquakes, introduces an exponent that the geophysicists call B, but you can translate it to an exponent epsilon for the energy. The Omori law is related to the temporal distribution, to the existence of aftershocks, the fact that earthquakes are not Poissonian, and measures the correlation of earthquakes, and also introduces an exponent that is called the Omori exponent P. Productivity law is a little bit the connection between energy and time. when you have a big earthquake, then you have more aftershocks. And this introduces an exponent which is alpha. And then there is a fourth law which is more modern. This was proposed only less than 10 years ago. That is called the unified scaling law, that has to do with the distribution of waiting times, so times between earthquakes. Okay? And this law is special because it's a double power law. It introduces two exponents, 1 minus nu and 2 plus xi. So we think that this set of exponents characterizes the criticality in this problem, and I will now revise them and see, so we can see exactly what do they mean, okay? So the Gutenberg-Richter law, you probably everybody knows. This was proposed by Gutenberg and Richter in the early 20th century. Originally, it says that the log of the number of earthquakes above a certain magnitude is scaled linearly with the magnitude, with a slope here b that is of the order 1. If you now use this relation between energy and magnitude, this translates immediately to a probability distribution for the energies that you record, which is a power law, has this shape E minus epsilon. And epsilon is related to B through this equation here. You just have to make the mathematics here. And then you get that epsilon, when B is 1, is of the order of 1.67, 1.66. Okay? And this, just for illustration, I have taken some catalogues from earthquakes in global, that means the whole world, or specifically for California or for Japan. And you see here the magnitude and the number of earthquakes for each magnitude. And this is logarithmic scale, so I am directly testing this. And this slope, this line here, is b equal 1. Okay, so you see that this is more or less true. When the distribution deviates from this law, in fact, is in most cases is because the catalog is not complete. So in some places they don't register small earthquakes, or they don't register all the small earthquakes. That's why we have deviations here. In fact, in California it's not plotted, but this continues like that because they have a better system for, it's not now everywhere is well registered, but many years ago in the 60s it was not well registered. And also the problems here in the right hand side of the tail are due to lack of statistics, because we don't have very big earthquakes many often, so that's good, but that's why you have these fluctuations here. Okay, so that's the Gutenberg-Richter law. Something that I want also to explain, that may be also for interest from some mathematicians or from other people trying to study critical phenomena, is how from the experimental data we can fit this value, because this is just a straight comparison, but we can fit the value from the data, and we use what is called the maximum likelihood method. This was method for power laws. It's very important to use this method because the standard least square fit will not work. It gives really very bad results. So when you have, this is the distribution, the power law distribution that is well normalized now with the epsilon, and the E0 is the minimum value that you need a cutoff in the lower part. When you do this maximum likelihood analysis, what you do is you put a cutoff in your data. You consider only energies above a certain minimum value, and then you compute this equation here. This epsilon is an estimator. This is the maximum likelihood estimator. This is the sum of the log of all the data you have divided by the minimum energy, divided by the number of data above this minimum energy, okay? You compute that, and this gives you, through this equation, the exponent. And this, I have shown here also pedagogically, is just from the previous data what you get. The idea is that when you get something which is really a power law, you have some flat behavior here. So it doesn't matter how you cut the data. So you just move this cutoff like this, and you can move the cutoff for several decades, and the exponent is stable. That's the idea. Okay, so you get this flat behavior here. Okay. Recently, we revised this method, and we also went a little bit further. So when you have a power law, you get a flat behavior, but you can also check that if you have a law that is a power law but has some kind of exponential correction, e to the minus energy divided by a certain typical energy, then the method renders you something which is not flat anymore but has a slope. So by this method we can discriminate, it's easier to discriminate here than in the histogram. When this is flat, it's a power law. When there is a slope, it's a damped power law. It's a power law with a damping factor, okay? Okay, in this paper, this is not important for today's talk, but we also studied what happens when you have a mixture of two exponents. So a probability law that is a mixture of two exponents, and then you find another kind of behavior with this method, okay? So after this parenthesis, let's continue with the other laws. The Omori law has to do with the time correlations, the fact that the sequence of earthquakes is not Poissonian. And this was discovered by Omori, I think in the 19th century, yeah, in the end of the 19th century, just by, after a big earthquake that he survived, he kept measuring how many earthquakes were felt every half a day. And that sequence has been kept until today. So they are in that place, in a very small, detailed place, how many earthquakes are felt. This is something is not rigorous because it depends on very much on where is your threshold. But he kept counting that, and you can see that if you plot number of earthquakes as a function of time to the original big earthquakes, that is called the main shock, this number of earthquakes decays in log with a line. This is again a power law in time that has this shape, okay? So the number of earthquakes at a distance t minus t main shock is 1 over t minus t minus t main shock to an exponent p which is close to 1, okay? There is a correction here to prevent the divergence exactly at the main shock, of course, but during the main shock, if there is something else, it overlaps with the main shock, so it's just not important, okay? But this is done for an individual earthquake. In a catalog, this is more difficult because one has to identify what are the main shocks and what are the aftershocks, okay? So this then there was it was proposed by Agnes Helmstetter, a way to do it. So essentially, when you have a catalog, what you do is you consider an energy window, and then all the earthquakes inside these energy windows, you consider this is a main shock, this is a main shock, this is a main shock, that's a main shock, that's a main shock, okay? And then these energy windows, we will move it later, up and down, trying to filter for the largest ones. But we do it in general with a small delta E with an energy window. Then you do that, and then for every main shock, you look for what is called the aftershock sequence. That is just the earthquakes that are smaller than this one. So in this case, it's only 2. In this case, you have these 2. In this case, you have a long sequence, and here you have short and short sequence. So essentially, you identify some sequences of aftershocks, define it like this, and then what you do is you overlap these times, starting from every main shock, and make a statistics. How many earthquakes you have on every bin, okay? And then you get this kind of plots, and then finally you move the window up. The idea is when you move the window up, the definition of aftershock is better because you are just selecting the really main shocks, but of course you lose the statistics. So then the data is more noisy. So then it's a matter of combining these two aspects. So then the idea is that the slope of these curves, when the window goes up, should be the Omori slope. This is the way we do it. And this is what we do with our data, okay? This is the Omori law. Then the productivity law is related to the Omori law. If you go back to this equation here, the productivity law refers to this constant K. This constant K is not constant, it depends on the energy of the main shock. And it depends on this energy with another power law now, with an exponent alpha. So if you want the number of aftershocks, if you integrate, I go back again, if you integrate that in time, you will get the total number of aftershocks from a main shock. If you integrate that, then the result is proportional to K. So that's the way to measure this law. So this number of aftershocks produced by a main shock with energy EMS is proportional to EMS, and by some special definition, it's 2/3 of alpha, okay? And this is this law here, forget about the red one, that tells you, measure it from a catalog, how this behaves. The combination of the two laws, the productivity law and the Omori law, when you plug this part here inside, and then you can put this constant in the other side of the equation, and you get that when you study different catalogs, you should have this kind of a scaling. So this energy, and also when you study different energy windows, the energy of the main shock to minus 2/3 of alpha times the number of aftershocks should scale like linear with t minus tms with exponent minus p. So in the same scaling, you have p and alpha in the same analysis. And this is what we will do with our data. And finally, the distribution of waiting times. So waiting times, also given a catalog, you can also define the silent times or the waiting times. There are different names. There are some small differences depending whether you consider the duration of the earthquake, but this is not relevant now. You take your catalog, you consider a threshold, and then you measure, you only consider the earthquakes above the threshold, and you measure the times between earthquakes here. And then all these numbers, you look for the distribution, the histogram of these numbers. Okay, so that's this D. Of course, it's clear that when you change the threshold, this distribution will change, because when you take the threshold down, these values will be smaller, of course. And also, it might change because of other reasons. It may be different in a different region of the world. It may be different in a different period, because there are faults that in a certain period they are more active than others, and if they are more active, these waiting times are smaller, and in general depends on many experimental factors, okay? But the idea is that all this dependence with experimental factors is hidden just in the dependence of the average waiting time. So if you compute the average waiting time, you can estimate it just by summing all the numbers, delta, divided by the number of events. You estimate that. You can see that this distribution, in fact, can be written like this. So it's just a function of waiting time compared to the average. And this is the delta D. Okay, so you have different catalogs, different thresholds, different periods of time. You get this kind of distributions. When you plot it like this, just multiplying here by the average waiting time, dividing by the waiting time, all these functions should scale and should behave the same. Now, the waiting time distribution, what is this unified scaling law? What is the shape of this function? Here there are two shapes. There are two possible shapes for this function. That this was proposed by Corral in 2004. If you consider regions in which the activity, the number of earthquakes per day or per hour, or it doesn't matter what is the scale, is more or less stationary, then you do this analysis and you get a universal function which has this exponential behavior here. It has a slope in the left and then exponentially like this. But if your catalogs are large enough in time, or they are restricted to a region which is small enough so that you are really exploring the changes in the life of that fault in that time, then what you get is a double power law. It's a double power law that has on the left this exponent, which is slightly slower than 1, and on the right this exponent that is slightly bigger than 2. This is what is called the double power law, and this defines these two exponents here. But to get that, you need really to have regions in which the rates are not stationary, they change in time, okay? So you have a rate mixture. In your analysis, you have a mixture of rates.
What is your x here?
X is this variable. X is this variable. Okay. This is phi of x. Okay, is the normal that is the variable that measures the waiting time against the average. Okay, divided by the average. Okay, so far this is what I wanted to explain from geophysics, because now these tools will be used for the problem that we are going to analyze. Okay. So let's go to the experimental aspects of our measurements. These are the two kinds of setups that we use. We call them, one is what we call load control, and the other is displacement control. Let me just go to some schematics here. Essentially, we have a sample, which is a porous material, which is between two plates, two compression plates. In the plates, embedded in the plates, we have some acoustic emission sensors. These are like microphones, but they sense ultrasounds, not normal sound, but ultrasounds. Okay? And then these two plates, they are driven by different ways. In this case, it's load control. What we have is the upper plate somehow is connected to a weight here, and this weight increases proportional to time. So in this case, the force is proportional to time with a rate that we control. And what we measure with a laser extensometer is the height of the sample that decreases, together with the acoustic emission that I will tell after. In the other experiment, this is called displacement control. The sample is here. We also have the embedded acoustic emission sensors. But what we do is to keep the machine compressing at a constant rate. So the height of the sample is proportional to time. It decreases proportional to time with a rate that is millimeters per minute. Here the rate was kilopascals or newtons per second or per minute. This is millimeters per minute. And then what we measure is with a load cell is the force needed to keep that rate going on, okay? So this is the two different ways we will do, and we sometimes compare the results of the two different experiments.
What is the choice of the sensor?
So then,
why did you choose ultrasonic as a frequency in which you want to measure acoustic vibrations?
well, you get, I mean, what you get spans more than ultrasonic. I will come to that now, but it clearly, there is a lot of interesting data between the 200 kilohertz and 2 megahertz, 3 megahertz. And this is, well, the setups are usually prepared for that. If you try to work on the audible range, you have, first of all, you have more noise. And here it's easy to clean the noise. If you go to higher frequencies, there is also electrical noise that couples to the space. So ultrasonic range is quite good for this.
Clean measurement.
Yes, to have a clean measurement. But you could go lower, a slightly lower frequency and still get the same, okay?
So this material is quasi-brittle rock?
You will see different, there's synthetic, and this will come. There are synthetic materials, there are biological materials. We have studied many different ones, but always they are, what the common thing is that they are porous. You will see, especially in the second part of the talk, there are two kinds of materials that give us slightly different results. Okay, so this is the acoustic emission, what you were talking, the acoustic emission detector. When you have some internal surface moving fast, this generates elastic waves. In fact, if this movement is very sharp, it generates elastic waves in all frequencies, because if this is instantaneous, then it emits in all frequencies. But then this propagates, and we register it here, we amplify, and then we keep that analyzing. This is a sort of a fast oscilloscope that records the data. Okay, this is the range where we work. And this is a typical signal that we get. It's a schematic, but the idea here is to define the parameters that we measure. So we have this black line is the voltage that we register, and what the machine is doing is, okay, it's taking data at 40 megahertz very fast, and just trying to measure this curve. And then from then, automatically the electronics is measuring. First of all, we need a threshold to define when the signal starts, and then we need also a way to define when the signal ends. And this is done by defining what is called a hit definition time. When the signal is below threshold more than a certain time, it means that the signal stopped. And this is something that we can control, but there's no way to separate events if we don't put that. Then from this signal, we can measure the starting time. We can measure the amplitude, which is the higher voltage. We can measure the duration. And we can also measure the energy by integrating it from here to here. We integrate it, the square of the voltage divided by the reference resistance, we get an energy. So at the end, from our train of signals, we get a catalog, exactly as with earthquakes. So we have at time tk, there was an event with energy ek, or amplitude ak, a duration dk. That's the catalog that we will compare with earthquake data. Okay, that's now your question. We have studied many different porous materials. What I will present today is essentially Vicor. Vicor is a porous quartz. It's synthetic. It has a structure that is porous at the nanoscale. At the microscale, in the microscope, it looks homogeneous and transparent. Okay, but it's porous at the nanoscale. It's produced by a phase separation process of a silica with another substance. Yes.
Sensor, it's a compressive force sensor or it's a shear force sensor?
It's essentially measuring the compression. Yeah, it's not a surface. But if you know about the sensors, they are neither one kind or the other. They always feel both a little bit. But the way it's also mounted is just to measure what comes from the below.
So you have a crack. The crack is generating a sound.
And this sound travels along the sample, then enters into the plate and reaches the sensor. That's it. Okay?
Is impedance matched with
The plate is usually steel. It's a steel, and the distance is 1 millimeter. The distance between the sensor and the sample. Okay, so I was saying that this is porous at the nanoscale. We have worked a lot with this material because, as you will see, the results are really very nice. They agree very well because this is a synthetic material. It's very clean. It's SiO2 in a 99% proportion. Okay. Then what happens is that this material now is not produced anymore. So now we had to change to other. Gelsil is a similar one. It's also SiO2. It's also synthetic, but it's made from grains of quartz that are sintered. Okay. So it's a different way. So and this gives also very good results, similar to Vicor, not as good, but similar. But then we also have compared with sandstone, which is a similar material but natural. It's just sand that has been compressed by geological history. We have also studied other synthetic materials, alumina, berlinate, even metals, many more. But I will focus today only in the last part, which is some results that I think that they were accepted last week. They will be published in 1 week or so, on the study of coal and charcoal. This will be the last part of the talk. Okay, so let's go first with Vicor. I want to see how is the time going. Okay, I am half of the talk. Okay, the Vicor results were the first system that we studied. You can find most of what I will explain here in this paper and some of the other ones. So this is just a summary of a typical experiment. Okay, so you have the height of the sample that decreases in time, and you can measure that with a rather good resolution with a laser extensometer. And this is, I'm trying to represent the catalog here. So this is logarithmic scale. So every time there is an earthquake, I put a line with the height of the earthquake. So, okay, there are many, so you cannot distinguish what's happening. But these are the real earthquake data, the real Labquake data. Okay, and here is just counting the number, the cumulative number of Labquakes. Okay, how it accumulates, that it increases. And below is, if you want, is the derivative of this curve. It's just the activity. We define a window, seconds or something like that, and then we count how many earthquakes in that interval of times. In this case, the total experiments last for 5 hours, for instance. And what I want to note here is that already here in these plots, in these two plots, you see that in our experiment, we are mixing different rates because we have rates that go from 10 to the minus 1 to 10 to the 2. We have 3 orders of magnitude. There are instances in which the activity is 100 times larger than others. Okay, this is important. So this is the kind of experiment we do. And also, in fact, in this curve here, you already see the Omori law. Because when you see, is there a chalk? Ah, no chalk. Ah, this. When you see a curve, a cumulative curve that is like this, and has this means there were many events, and then after that there was this curvature. This means that the activity is like this. And this is nothing more than the aftershocks. Okay, so you already here, you see that when you have this kind of steps, which you look like this is it's not Poissonian. It cannot be a Poisson process at all. Yes?
My question is that all your materials are brittle or quasi-brittle. If I have to do with metal, ductile metal, then in the plastic zone, where you have the non-linearity, should I see this avalanches or there?
We did nickel titanium metal, but porous.
I see.
Porous nickel titanium,
So
highly porous.
it is becoming
It's a sort of mixture of what you are saying. What I am measuring is like a cumulative mixture of small events which are of your kind.
No, my question is that if I have to do the stress-strain curve, then in the stress-strain curve,
You will see.
where I will see.
You will see, but not in this experiment because here we are controlling the force and we measure the height But then in the next experiment in which we control the displacement, you will see the stress strain. There are two kinds.
Is a large drop, that is a bulk fracture of the material?
Yeah, there's usually, in Vicor, usually you have some small drops. I am talking about macroscopic measurement of height. Some small drops, and then typically there is one, which is this brittle fracture that you expect. But note that the largest events may not be here. Sometimes they are there, you see these ones. And also the largest activity, you have peaks of activity very large here. And also here, of course. And also another thing to note is that after that, there's still activity comparable to what you had here in the beginning.
So how does one understand that the system is having a bug?
It falls about failure, but what is left keeps resisting because you are increasing the force proportional to time. Okay? And that's it. That's what happens. Yes?
The resistance that the material offers is proportional to the pore size, right?
The
resistance that the material offers is a function of the pore distribution and the size of the pores.
Yeah, but these pores in Vicor, they are really in the nanoscale.
Right. So you mentioned that it is a synthetic material that is made by extrusion process.
No, it's made by a phase separation process. So it's really, I don't know exactly, but it's in the liquid phase. The silica is liquid. It's mixed with another liquid material, I don't know which is, that they want, then at high temperatures are mixed. They decrease the temperature, and then the liquid, they want to phase separate. And then when they start phase separating, they stop this phase separation at the point they want to get this intricate structure, and then they cool, and then they leach their second material. And what it get is a skeleton of silica. But you can get a similar structure, just a sintering powder.
But it's statistically isotropic.
It's isotropic. It's rather isotropic, yeah. I mean, you cannot discard that some of the samples have some anisotropy, but it's rather isotropic. Okay, well, you can also see here again the cumulative number of events and how the size, the height of the sample is decreasing, and these circles, they show some proportional to the log of the energy of the event. So you see that this big failure usually are generated by a big event. There's a big event that generates this sequence of aftershocks, okay? Okay, so, well, I can skip this one. Let's go to the test of the laws I was saying before. If you look for the Gutenberg-Richter law, you just make a histogram of the number of events as a function of the log of the energy, and you get this nice Power law. There is an advantage here that we don't have with earthquakes, that is that we can control the rate. In earthquakes you cannot do, but we can do analysis at different rates, and you see that the exponent is not very much dependent on the rate, except if you go very fast. When you go very fast, you start overlapping avalanches. The acoustic emission setup cannot distinguish them, and then you get distortions of this distribution. But there is a range of compression rates that gives a stable exponent, okay?
But this exponent is different from 1.67.
Yes, this is important. The exponent is around 1.4, 1.35, and 1.36. You will see. Depends also. It's slightly different in the two mechanisms: the load control and the speed control. You will see. But it's not 1.66 in this case of systems. You will see, because these are the brittle ones. Okay, this is the measurement of the exponent by the maximum likelihood method. You see this flat plateau here that extends 4 decades, something like that. If you go too fast, then there is something which is not flat. Probably you are introducing a certain overlap of the avalanches. We call avalanches these kind of events for reasons that maybe I will explain on Thursday. Okay. Stationarity, this is also important for you that are worried about that. So if you, let me go back. If you go here, you take windows of 3,000 seconds, and in each window you evaluate the Gutenberg-Richter exponent. These windows are taken without looking at where the big events are, of course. If you do that, you see these are different windows, all of them the same slope, stationary. Except maybe in the very beginning, when there is an adaptation of the sample to the, so the first few seconds are different, but of course we don't have also statistics to check that. But if you take reasonable big windows, you get a stationary power law, which is different from many models that have been proposed. Okay, something that we studied recently in this paper here with Jordi Baró from the Mathematical Center near Barcelona is not to take windows like this at random, but just to take windows that end in a big event. So essentially, we recognize in this sequence of events where are the big ones, in this case the five big ones, and then we consider the approach to this event, the approach to this event, the approach to this event, and the approach to this event, and we overlap that, and we make the statistics. So it's like trying to study the foreshocks. And then what you find is that now this is measured as the distance to the big event, it's in pressure. So it's the pressure minus the pressure to the big failure divided by the pressure of the big failure is normalized. You see that the exponent is still stationary towards that. This, I know that there are models that they don't say that. The average energy is stationary, so this suggests that the distribution is also stationary, but what is different is the total energy release. Why? Because the energy release as a function of this force is the average energy times the number of events, and this is what is increasing. Essentially, you have an increase of the activity, not of the distribution of energies. Not the exponent, just the activity. This is what you find in this kind of samples. And this is for Bicor, and this is for the similar health seal sample. Okay, then you can also test the other laws. You can test the Omori law. Now the extra difference here is that we can control the rate. So we have experiments at different rates. And then we have these curves here for the different windows, are the different colors, and the 3 panels are different rates. We get Omori exponents which are not really very similar to they are smaller than the earthquakes, but this probably has to do with the problem that we are not locating really where the events are occurring. We don't have location. So then we are considering the whole sample, and then probably what we classify as aftershocks are not really aftershocks. This could be one of the explanations that we are trying to solve that. But then when you scale, you go to what I proposed, the combined scaling. You first scale by the rate, by the average rate, and you see that all the curves that have the same color, they overlap, and then you introduce here the law for the productivity law, and then everything scales. And here you play with the exponent alpha until everything scales, and you deduce alpha. Also, the method of fitting alpha is the scaling. This also always has larger error bars than a method of like maximum likelihood. But it's the way we have to fit alpha. So we get alpha and we get p from this scaling plot, okay? And now the unified scaling law, I have already explained it. We get this double power law. These are different, moving the threshold up and down. So we get more sparse or more joint data, and also changing the compression rate. Everything scales very well just by this average or inverse of the average waiting time or average rate. And you get these exponents, and on top of this data, you can overlap earthquakes data. So this green data is California catalog, and overlaps with rather the same exponents here, 1 minus nu and 2.45. So clearly, at this level, the two phenomena are described with identical laws, okay? Okay, now I have some extra things, like for instance, what happens when you have displacement control? So you keep the speed moving, then what you get is this force. Well, you cannot see it very well, but it's this force. You see this line? This is the force as a function of time. Time now is x, because x is proportional to time. So this is displacement and force. You see that there are these events, and there's a big one, but it keeps going here, you see, keeps going, okay? Well, in this work, we also tried to compare the energy of the big events with the force drops. You can go there. The correlation exists, but it's not really very big. But we also checked that it's stationary in this case. And the exponent, here are different samples. Here what we tested is the aspect ratio, because I know for the people that work in fracture, The aspect ratio is very important. This you have in this data is not ordered by aspect ratio. It's just you have aspect ratio which are 1 to 6 and others which are 6 to 1. And the exponent is rather the same. The variations you have are more like sample-to-sample fluctuations. So everything is around 1.3 something, 3.5. The other one was 3.9. This variation, we are not sure whether it's just sample-to-sample or there is really a smaller exponent when you have this displacement control. But apparently, at least if it's a very tiny difference. Could be also related to the fact that the overlap of the avalanches is not equivalent when you have force control than when you have displacement control. Okay, and that's just, yeah, now I am getting out of the time, I think, but let me check. No, still. Oh, sorry. Just this something that also did recently was to try to see how far we can go in scales, okay? We did experiments, these 4 experiments, with different amplification factors. So what we do is to focus on energies in different ranges, and we get these histograms, and then the people in the mathematical research center, they found a way to do a maximum likelihood fit of all the data together that have been worked in different ranges of energy. And then this is for amplitudes, so just the height of the signals. You get this nice power law with 4.5 decades, but for energies, we get almost 9 decades of power law. The same that they get in earthquakes, almost. But, of course, earthquakes at here, we are there, 30 decades below. But this, okay, this is what we got. And it's true that this exponent is, again, it's still the one that fits not the same as earthquakes. So the 2 slopes, they don't fit so far. Okay? Now, let me go to the last part, very fast. But now you understand my language very well, so I can go fast. Very recently, we did this study of coal samples and charcoal samples. This, coal, it's a complex, I don't know if it can be called a molecule, but it's essentially made of benzene blocks, carbon and hydrogen, but it also contains oxygen and nitrogen and some other stuff there. There have been some people trying to describe these molecules. It's rather impossible. This is at the molecular level. If you go to the microstructure, what happens is that this is not a mineral. It's not in fact, it's more a biological substance than a mineral substance. And in a rock, you distinguish minerals. In coal, you distinguish something which are called macerals. Macerals is equivalent to minerals. And macerals means different biological origin. So essentially, you have 3 kinds of macerals. You have vitrinite that comes from the wood and the leaves. You have inertinite that comes also from wood and leaves that suffered typically a forest fire before falling and being buried. And this changes the chemical structure. And liptinite typically comes from some fruits, the pine tree fruit, and also some algae and some other stuff that it's much more rich in nitrogen. They can distinguish that in the microstructure, the experts. I am not an expert in coal, but we worked with Maria Angeles Borrego on that, and they know very well. And, okay, it's highly porous also, with even cracks that you can observe almost by eye, but it goes down to nanopore also, because it comes from the cellulose structure and so on, and it's layered and everything like that, okay? These are just the optical microscopies, optical microscopy images of the different samples we have studied. And what I just want to point out is that these samples, they go from highly heterogeneous, you see here, highly heterogeneous with big holes, etc., to much more homogeneous. All this is coal, okay? And this is because this evolution when being buried, when this material evolves, is what they call the rank of the coal. All the different macerals become more and more equal, and you cannot distinguish them anymore. They also lose porosity at the microscale, but win porosity at the nanoscale. So this somehow is more similar to Vicor, because it's porous at the nanoscale, whereas here it's porous more in the macroscale and highly heterogeneous. Charcoal is special because charcoal, in fact, cannot be classified as a coal, because it's only the wood that has been burned. And it has this structure here, which is very similar to this here, and some of these parts here. These are the inertinite. The inertinite macerals are very similar to charcoal. So essentially charcoal is if it's only one maceral, which is inertinite, that has not been compressed. So still keeps the shape of the cellulosic tissues of the wood, okay? But this is, let's say, the most heterogeneous one, and we go down to the, okay, I go very fast now. So we have this gradation of samples. These samples can be studied very well with composition, etc. But we can order them from very heterogeneous to more homogeneous by different methods. Essentially, and now is your answer to your problem here, we can classify, you will see there are two kinds of behavior. In this case here, you see force against a strain, okay? You have this elastic part, and then it starts to fail, and then there is a brittle failure, PAM. And this is the acoustic emission, the activity, number of events per time. But in other samples, you have this. It goes elastically, and then it starts to decrease like that. For a long, this is much longer time than here, or much longer strain than here. It supports much more strain in this case. These are what we call hardening material, hardening samples. I call it hardening. I don't know if this is the common name, because after failure, in most of the occasions, after failure, the sample is able to go to larger forces. Whereas I call this one weakening, because after failure, the sample does never recover that force. So you see this slope here, whereas here, that's it, essentially. Okay, we have these two samples, yeah.
But in all these samples, you get that unified scaling law?
You will see. Now it comes. We can take all our samples and group them according to whether they show hardening, group 1, soft weakening, group 3, okay? Charcoal is here, okay, in group 3. We have this weakening, and of course we have some samples which are in between that we cannot classify. They show parts which look hardening and parts which look weakening. It's true that these are the more homogeneous samples. For COA language, this means high rank samples or high vitrinite content. And in group 3, these are the more heterogeneous samples, and in particular charcoal. So highly homogeneous hardening, very heterogeneous weakening. And then we do the analysis of all the two groups, and we compare. What do we find? The Gutenberg-Richter exponent, maybe you cannot see it here, but forget group 2. For group 1 is 1.4. For group 3 is 1.66, the earthquake exponent. From group 3, the heterogeneous sample, the Gutenberg-Richter exponent is 1.66. Okay, you see here, these are 1.4. This is much higher, 1.6. In particular, charcoal, which is what we call the prototype sample exhibiting, in this group 3, exhibiting this weakening behavior. This is rather flat. It's the blue data. It's rather flat for several decades. Okay? And also in this case, we can test, this is charcoal. In charcoal, we can test that the slope, this 1.65, is independent of the compression rate. Now it's millimeters per minute. You see always the same exponent. You can check Omori law and productivity law. You get the same exponent alpha, but different Omori exponents. And also, this is independent of the rate. And for the waiting times, you get the double power law. And here is one of the messages, is the same values everywhere. So it seems that the double power law, of course, we already saw that was similar to Vicor and earthquakes. It's the same for everything. So it seems that these two exponents, 1 minus nu and 2 plus xi, are more universal than the Gutenberg-Richter exponent. Okay, and that is the take-home message of this second part of the talk. Sorry, because I was rather fast, but just, so this is a summary of the exponents. So essentially, earthquakes and heterogeneous samples that show weakening have the same exponents. Samples that show hardening have the Vicor exponent, 135. Here is 1.66. And then the other interesting message is that the 1 minus nu and 2 poxy is the same everywhere, always. So this law, this double power law, seems to be really very universal, despite that the Gutenberg-Richter law is different from one class and the other. Okay? So, and that's just the conclusions. So essentially, we have shown that Labquakes show lack of characteristic scales revealed by the Gutenberg-Richter distribution, the Omori time correlations, and the double power law distribution for waiting times, and also that from the analysis of coal and charcoal, we have seen that there are two classes, materials exhibiting weakening during failure that include charcoal, have an exponent 1.66, rather similar to earthquakes, whereas materials exhibiting hardening, that compare very well with Bicor, they have an exponent which is 1.35, and the exponents characterizing the unified double power law seem to be the same for both classes. And that's also, thank you very much for your attention.